Swayam Prabha. Digital India. Educated India.
Okay, so now we will start with our study of dynamic games, and the key issue we will now begin to tackle is the issue of information. Okay, so first let me ask you this: I kept mentioning that in all our games, the players were playing simultaneously. So when do you say that players are playing simultaneously? So let's take the example that we had looked at in the last class, right? It was this game of matching pennies. I had looked at the asymmetric version, but here's the symmetric version. So the game of matching pennies with a symmetric version is something like this. These are the payoffs. So the players have to put down a penny, a coin with either heads up or tails up. Okay, and if both players put up the same face, then player 1 gets 1 and player 2 gets -1. If both players, if one player puts up heads, the other player puts up tails, then player 2 gets +1 and player 1 gets -1. Okay, this was the situation. Now, what this game obviously is meaningful if so this was a simultaneous move game. So what does it mean for players to play simultaneously? Okay, so simultaneous, if you think about it in its English meaning, it would mean that they are actually putting the coin down at the exact same instance. Okay, so physically at the exact same cosmic time, that's when they are in fact putting down the coin. But that is not, so the game remains strategically the same even if they put the coins down one after the other, but without knowledge of what the other one has done, right? So what we mean by simultaneous really is that the players do not know what the other player has done. So simultaneous in a game theoretic or strategic context has not so much to do with time as it is to do with information, right? If players do not have information of what the other player has done, then it is as good as simultaneous. Is this clear? Okay. So now consider the following. Let's take another game. Okay. So let me just write out whatever I just said, that this is simultaneous. When we mean that it is simultaneous, really means players do not know what the other player has played. This is what it means for a game to be simultaneous. Okay. Now, here's another game. This is actually a game with infinitely many strategies for each player. So a player, suppose there are two players that are producing some homogeneous good, two firms, let's say. They produce a homogeneous good. The homogeneous means a good, they are producing a commodity or a good that can, genius. A good is homogeneous means that the one that is produced by the thing that is produced by one player is indistinguishable from that produced by the other. Okay. So what matters is how much they produce, not what they produce, so long as they are producing the same thing. Okay. So that means so examples are, for example, electricity. Electricity produced by one plant is the same as the electricity produced by another plant. You don't really distinguish between the electrons coming from one plant and the electrons coming from the other. So so this sort of a good is a homogeneous good. Many of the other things that we that we use on a day-to-day basis are homogeneous. cereals, rice, wheat, etc. They are, it doesn't matter whether this come from this farm or that farm, so long as the breed of the rice is the same, it is the same rice, right? Okay. So that's not the same in other goods, like for example, shampoos will be different for shampoo made by one company will be different from that made by the other company, toothpaste made by one will be different from the other, cars, etc., etc. Those are not homogeneous. So one thing that we know about when goods are homogeneous is that what matters is the total supply of the quantity in the market. That determines the price. Okay, and the price can be characterized usually by some sort of a formula. You would kind of know how the price would behave as a function, the market price would behave as a function of the amount of quantity produced. Alright. So in this case, so we have two firms producing a homogeneous good. Suppose Qi is the quantity produced by firm I, and let us say that the price, okay, the price in the market is a function of the quantity is produced by both. So it is a function of Q1 and Q2, and so I am going to, and I will assume it takes a very simple form. I will assume that it takes the form 1 minus Q1 plus Q2. Okay. So this has been normalized to eventually give you this sort of form. Okay. The price is 1 minus Q1 plus Q2. So it is a function of the total production. Okay, that is Q1 plus Q2. So if this is what the firms are faced with, then the firms have what they would do is each firm wants to maximize its profit as a function of its profit is a function of Q1 and Q2. So that would be equal to 1 minus Q1 plus Q2, which is the price, times the quantity it has produced, which is in this case Qi, minus the cost that it incurs in producing it. Okay, so then let us suppose that is C times Qi. Okay, so this is this is a cost. Okay, so this is per unit cost per unit quantity. Okay, so this is what these firms produce. This is what the objective of each firm is. So each firm would like to now decide the quantity it should produce in order to maximize this profit. Okay. Now, when the firms are trying to decide their quantities simultaneously, then essentially what they are doing is they are trying to decide what quantity they should produce without knowing what the other would be doing, right. So then what would be the way we would solve for this, look for a solution for this sort of a situation through the Nash equilibrium. So can you tell me what would be the Nash equilibrium of this game? So this Ui is actually, you can see, is actually quadratic and concave in Qi. Okay. So you can solve for this. Can you tell me what it would be? So let's just differentiate this. So let's write this for U1 and U2. So let's differentiate this and put this equal to 0 with respect to Q1, and let's also put this equal to 0. What do we get here? So I will get yeah. Can you tell me what this would be? So this will be 1 minus 2Q1 plus minus Q2. Yeah, this should be Q1, sorry. This is Q1 minus Q2 minus C equal to 0. and then a similar equation for the from the second one would give me 1 minus 2q2 minus q1 minus c equal to 0. Alright, so let's solve this simultaneously and tell me what you get. 1 minus c by 3, right? Yeah. So q1, you get q1 star equal to q2 star equal to 1 minus c by 3. Okay. So this is the Nash equilibrium. So the Nash equilibrium of this, of the game, where if these players were playing simultaneously, would be that they would each choose these quantities, 1 minus c by 3. Okay. Now let us take this one step forward and let us ask, what if player 2, what if this game was not simultaneous? Okay. So what this means is, suppose player 2, okay, suppose player 2 can observe, suppose player 2 can observe what player 1 plays. If player 2 can observe what player 1 plays, okay, then what is the strategy of player 2? So let me go back here. So first tell me, here in this game, what were the strategies of the players? They had to decide the amount of quantity to be produced. So what is the space of strategies? In this case, it would be said, well, I have not said it explicitly, but it's all non-negative numbers, right? Basically the space of strategies is 0 to infinity. Here the space of strategies is for each player. Okay. Now what is the, now here player 2 can observe what player 1 plays. Okay. Player 2 still has the same objective, it is still profit is still given by the same formula. Okay. So he is still the amount, the price that will come in the market is still going to be 1 minus q1 plus q2, alright. The cost is still c times q2. So on the face of it, nothing seems to have changed in the problem in terms of its specification, right? It seems like, well, the utility function is, the profit expression is still the same, the price is the same, the cost is the same, but somewhere something has changed when P2 can observe what P1 has played, right? Because when P2 can observe what P1 has played, he will obviously play differently. So where is that manifested?
Not necessary that where the derivative is 0 is necessarily the argmax of.
Why?
Well, because we haven't checked it down.
No. So what are this? Let me ask again this question. So what are the strategies now of the players? In the earlier case, the strategies of the players was 0 to infinity. Now what are the strategies of the players? Okay, very good. Why? Right, right. So what are the strategies for the players? See, this is your first introduction to a simple dynamic game. This is a dynamic game is one where players have there is some player who has some information which is different from another player. In a simultaneous game, every player starts with all players start with basically null information, zero information, with right. Whereas here there is player 2 who has the information of what player 1 has played, and when he has this information, it makes sense that he picks his quantity then as a function of that information, right. If he had say here in this case, the information is the amount of quantity that player 1 has produced. If the information was something else, like for example, it was the information is about the weather or something like that, which player 1 did not have, then he would pick his quantity as a function of that, right. So, the point is that now that a player has some additional information, his strategy is not merely to decide how much quantity to produce, but it is to decide how much quantity to produce as a function of what he knows. So, the strategy is not really the quantity, the numerical quantity itself, but the function that maps his information to a quantity. Okay. So, the player 2's strategy now, is a function from 0 infinity to 0 infinity. So, here we distinguish between two different terms. So, this is what we call a strategy in a dynamic game. The quantity that he actually produces, and that is what in fact eventually influences his cost and his eventually influences his profit, is that is what is called action. Okay. The quantity that he produces is the action. So, Q2 here, this is his action, and Q2 is chosen as a function of his information being Q1. So, let us call this function gamma 2. This here is his strategy, and it is chosen as a function of Q1. This here is his information. Is clear? So, so strategies now are, whenever you are in a dynamic game, strategies now necessarily become functions, okay, because there is someone has some information which is non-trivial, right. So, the strategy for that player is a function then that goes from his information to his action, all right. So, the immediate shift that you see when you go from a static or simultaneous move game to a dynamic game is that the problem necessarily goes into function space, because now everything has to be dealt with in the space of functions, all right. So, those of you who have taken my stochastic control course, you would have seen this over there as well. When we write out, we cannot write a stochastic control problem in terms of only actions. You have to write it in the space of policies, right, and the space of policies there is basically again the space of functions, okay. So, then the reason for that is again because stochastic control is about, at the end of the day, about information. It's about what information you have at each instant in time. So, because you have to map that information into an eventually a control action. This issue is usually moot in the case of deterministic control, because there you have to simply take a sequence of actions, and the information is available to you as a look ahead because of the lack of randomness in the problem, right. Okay, all right. So, I will not go into those digressions, but the point is so now that now that P2 knows Q1, it makes sense that he tunes the quantity that he takes based on what Q1 is, and you have to allow for him to have that flexibility, and so therefore, his strategy then is a function that maps Q1 to Q2, right. So, the space of strategies then for player 2 is then the space of all such functions. space of strategies let us call it capital gamma 2. This is these functions gamma 2, gamma 2 maps now. What is the space of strategies for player 1? Yeah, the space of strategies for player 1 is still to pick a quantity, right? He has no information to start off with. So, there are two different questions here. One is, what is the space of strategies? Okay, means what is the allowable space through which he is picking his strategy. The other is, what is the optimal strategy that he should be playing. Okay. Now I am not asking you what the optimal strategy for player 1 is. I am asking you what is the space from which his strategy has to be chosen. And the space from which his strategy has to be chosen is simply a quantity. Player 1 has to pick a quantity, player 2 then observes that quantity and then decides. So, in terms of, the strategy for player 2 is a plan effectively, right. It is a plan which says that, okay, you know, if player 1 produces 100 quintals, I will produce so much. If player 2 produces 200, player 1 produces 200 quintals, then I will produce so much. Player 2 produces 300 quintals, then I will produce so much. Essentially, for every value of Q1, he has a response planned, right. He has a plan that gives him a quantity to produce as a function of what player 1 would hypothetically produce. Player 1 does not have any need to make such plans, because he has no, there are no contingent informations there is no contingent information for him. He is the one who starts the game. He plays, player 2 observes and player 2 responds. Okay. Now, that does not mean player 1 does not have to strategize, that is a different matter altogether, but he does not need to have a contingent plan which says that, this is my information, then this is what I will do. If that is my information, then that is what I will do, etc. So, player 1's space of strategies for player 1 is, this is still 0 infinity. Okay, all right. Now that we know that these are the space of strategies for the players, so now tell me, how should these players play? Okay, so now P2, so P2 does, so he will find P2 looks for a quantity such that Q2 star such that if he looks at his utility from Q2 star, that is better than playing any other Q2. Now, this looks oddly like the Nash equilibrium, but is there something that I have that is different? Yeah. So, a potential mode of play is what I am writing here. So, what P2 could do is that he could say, well, I will play a Q2 star that maximizes this expression, and in this expression, what do you observe about Q1? Q1 is not fixed at a starred value. So, this is just some value of Q1, right. So, he is going to just take up a hypothetical value of Q1, find whatever is the maximizing Q2, right, maximizing Q2 from here and take that as the Q2 star. So, so then as a result, Q2 star will necessarily be a function of Q1. Is this clear? So, this is the dependence, the functional dependence that we just said. So, a potential mode of play for P2 then is to say, well, he could play this strategy gamma 2 star, let me call this gamma 2 star, where what is gamma 2 star? Gamma 2 star is that gamma 2 star of as a function of q1 produces a quantity q2 star, where q2 star satisfies this, right. So gamma 2 star for every q1 will it specifies the quantity q2 star which optimizes this. Is this clear? So Q, yeah. Okay. So now with this in mind, so this is the mode of play for player 2, and what is the mode of play for player 1? If player 2 is going to play gamma 2 star, which is basically specifying the quantity that maximizes his utility as a function of q1. Okay. Now what is the mode for how should player 1 play? Okay. So a mode of play for player 1 would now be see like she asked, does player 1 know that player 2 is going to respond, okay, or player 2 does player 1 know that player 2 can observe player 1's quantity? Well, so this is that is known to player 1. So if the players know that this is what will be known to them, okay, during the game. So now that player 1 knows that player 2 is going to respond with gamma 2 star, what player 1 should then play is, well, he can say, well, he can essentially anticipate that is going to be the response of the player. Okay. So a potential mode of play for player 1 now is to play q1 star. So let me use star here so that there is no confusion. Okay. So what player 1 would then say is, he plays a quantity q1 star such that it maximizes the utility that he would get, assuming player 2 would respond with gamma 2 star. Okay. So assuming taking q2 as to be equal to gamma 2 star of q1, he maximizes this over q1. So you see one thing that has happened here. So there is now a dependence here. The quantity of the other player is not just the quantity that the other player is producing is not fixed in this optimization. The quantity that the other player is producing now is a function of what player 1 would produce. So player 1 is anticipating that player 2 is going to respond in an adaptive way. So he is going to adapt to whatever quantity I produce, and so keeping that model in mind, he optimizes he maximizes his profit. Is this clear? So he is maximizing this, knowing that q2 star is a function of knowing that q2 star is a function of q1. Okay. So now in a game, we always assume that the utilities are common knowledge. We assume that who knows what at various times, who would know what during gameplay is also common knowledge. So gamma 2 star is something that player 1 can in fact compute on his own, right? He can compute that is what the player 1 would play, and then respond, and then as a result he can then compute this whole expression. Is this clear? So he can compute this and get his q1 star.